let's get this second half of the day of particle physics underway. Will you please welcome him back to the ISS stage, Dr. Martin White.
Thank you. Okay, so we have part two, very much following on from this morning. And as I've been complaining to Chris all day, I flew to CERN for a week last week or so. So I'm extremely jet lagged, and I tend to fall off a cliff at some point in the next hour. So we'll see how we go. The first lecture this morning, remember, was mostly theoretical. I was covering the Standard Model, what underpins the Standard Model, what we understand in nature. What I'm going to start this lecture with is why the Standard Model can't be the final answer, and what might be next. And then I'll talk about the experiments that we need to do to find that stuff out. So as I said this morning, I do both experiments and theory, and I think that's a great thing to do, because you'd end up really understanding why you're doing the experiment, and then you really understand what you're looking for. And as I go through, I'll sort of make clear the sorts of jobs you can do in science that don't just involve one or the other. There's lots you can do. So this morning we saw the particles of the Standard Model, and we saw that we're mostly made of this stuff, and we can make these sorts of things in colliders, but they decay. We spent a long time thinking about force particles, and what it means to have a force particle, and people asked very difficult questions, which I half answered, about why there's 8 gluons and things like this. And we found there was a Higgs boson. But notice that now we've discovered the Higgs boson, there is nothing left in the Standard Model to discover. Right? The theory told us there had to be something like a Higgs boson. And if we hadn't seen that at CERN, we'd have seen something else that explained how the weak gauge bosons get their masses, the W and Z bosons. So naively, there's nothing left, apart from gravity, which might be so high energy we never see any quantum gravity. There's nothing left to discover. So what is it that makes me think that there is something there that we have to discover? The first thing is that the Higgs mechanism is just totally made up, right? And you might say, but all of it's made up by somebody, and that's true. But there's a specific type of made up which I'm talking about. We learned that forces are something to do with symmetries this morning, and it turns out there's a deep connection between the Higgs boson and symmetry breaking. And in every other example in nature where I see a broken symmetry, I understand why it's broken. So a classic example is a magnet. You probably haven't studied enough magnetism yet, but at high temperature, a magnet isn't really magnetic, and as you cool it down, all the sort of spins line up and it becomes magnetic, right? So you can actually change the magnetism of something by changing the temperature. And that's because there's a physical force, magnetism, giving rise to that sort of behavior, and we understand it. In the Higgs case, they literally just made up that equation that I showed you this morning. Now, bizarrely, what we measured at the LHC seems to be more or less that equation, but it is totally made up, right? So I'd like to understand where that came from. We have ideas. Maybe the Higgs is a composite particle. There's a great complication in the Standard Model that the mass of the Higgs, which we've measured, should actually be a billion times bigger, because the same sort of weird quantum effects I showed you this morning act to increase the mass of the Higgs. I spent this afternoon with the particle physicist over there chatting about a new idea about why the Higgs is so light. We think we've discovered a new mechanism for this. But it's very mysterious, right? Why are there 4 forces in nature? Why are there 4 different ways of sticking our Lego blocks together? Why not just one force, right? One force would be by far the most natural explanation. And indeed, if we have a grand unified theory, when the universe is born, there is just one force. And it's as the universe expands that it sort of separates into different forces. But there should just be one force. And if that's true, there's physics that we can measure at the LHC that tells us that this is the case. So LHC, when I say this, is Large Hadron Collider, just for completeness. We saw this morning that gravity is not in our current theory, right? So we need to add gravity. Now, at some point, that has to change the theory. It might not change it in ways that we can measure down at low energies, but it does have to change the theory. And finally, we had this issue of extra dimensions. You know, string theory only works, probably the best idea we have of how to do quantum gravity. It only works in something like 11 dimensions, right? So where are these dimensions? You know, when I'm moving my hand, I mean, we think there's 3 space dimensions. There's this one and this one and this one, and there's a time dimension. But if we have these extra dimensions, there's this idea that they're curled up. As the universe expands, it sort of curls up these extra dimensions. Now, amazingly, there are graphs we can plot from the LHC data that would tell us if we had extra dimensions, right? So we can discover them if they're there. This came up in the Doctor Who show. The TARDIS works by exploiting extra dimensions, and it's possible indeed that they're there, right? There's another mystery which Lawrence Krauss, I'm sure, told you all about, and that's dark matter. So when I was a kid in the country, you know, I genuinely thought that it was the points of light in here that were the interesting thing to study in the universe. You know, there's stars, galaxies, there's all sorts of stuff here. And of course, the house is quite interesting as well. You know, people, the origin of life, still a great mystery. But actually, what we've now discovered is that it's the gaps between those dots that are even more interesting. There's a weird dark matter filling large amounts of the universe, and we'll see how much in a minute. And we literally have no idea what the stuff is. So did Lawrence Krauss tell you about dark matter? Yeah. He did. So I'm probably going to tell you the same things, and hopefully from a slightly different angle, and then we'll talk about how we measure this stuff at the Large Hadron Collider. Why is this not working? It's still a bit useless. Okay. So did he show you this picture? No. Yes, some say yes, some say no. Okay. Some people were looking at Facebook at the time. Okay. The first evidence of dark matter came from this chap. This is Fritz Zwicky, who by all accounts was a totally obstinate man, and I can well believe it from this photo. Right. Basically, you can watch galaxy clusters going around each other, and they sort of orbit like this. And in fact, it's Kepler's law that gives you that motion. So it's the same as Newton's law. Kepler was the first person to write a formula which connected the period of an orbit to its radius. And you can derive it from Newton's law. It's one of the first really cool derivations that you do. It's called. Have you done that, in fact? Maybe not, but you can do it, right? So if we look at the visible matter in these systems and we watch them orbiting, we get curve A, right? That's the curve that we get from Kepler's law. What we actually see is curve B. So there's two options here. One is that there is, you know, something very, very wrong with the theory of gravity, but people still look at this idea. It's very hard for gravity to be wrong for galaxy clusters, but right for everything else, right? That's very difficult. It's more likely that there's just some mass there that's not visible to us, right? If I had more mass, you know, so I sort of said earlier that I didn't want to look at this. I probably do. Remember Newton's law for gravity is F equals gmm over r squared. So if I have a bigger mass, I have a bigger force of gravity, and I can get something like curve B, right? So it's not outrageous to suggest that there's matter that's not visible to us. I mean, how do we see things in space? We see photons. You know, we use a telescope, and it might be an X-ray telescope, it might be a gamma-ray telescope, we'll see those later, but we're seeing photons. So if there's matter that doesn't interact strongly with photons, we wouldn't see it. It would be dark matter, right? Anything that's electrically neutral doesn't interact strongly with photons, because photons are the particles of the electromagnetic force, so you have to be charged in order to interact with photons. So you can have an indirect interaction with photons, which is a bit more complicated through loop-mediated processes. There's a complicated bit of physics. Basically, I might not be charged, but I might interact with something else through another force, which is charged, and then that thing could produce photons. But that's then weaker, right, than the original interaction with photons. So the idea that you have dark matter isn't wacky, right? Rubbish. This doesn't interact with photons either, it turns out. Right, there's more strange evidence. Did Lawrence tell you about gravitational lensing? Yes. So amazingly, so he told you about general relativity. This is Einstein's theory of gravity. It's a classical theory, right? This is the problem is, how do you make general relativity quantum mechanical? That's what we can't figure out how to do. But it tells you that gravity is the curvature of space by massive objects, right? So you know, the classic example, which Lawrence may even have told you, is I put a heavy ball on a sheet, and it sort of bends the sheet. And then if I roll a ball bearing in, it will orbit, right? And it's actually a thing moving in a straight line, but it's moving in a curved space, right? So it looks like it's moving in an orbit. And that's what general relativity tells us, is what's actually happening around the sun. The sun bends the space in the solar system, and the Earth's traveling in a straight line in a bent space, right? So that's basically saying that mass acts like a lens. A lens is something that bends light because it has some non-trivial refractive index. And so you can basically use massive objects as lenses, and there's a great diagram of that here. So what we're seeing here is that we have light, we have a massive object here, here's the Earth. Light here that you know, can reach the Earth and is hardly touching the field of this object comes to us straight. Light from here shouldn't be able to be seen from the Earth, right? Because it would be flying off in this direction, or it would be stopped by the object. But what actually happens is that it's bent around the object, and so you actually see it. And we can literally look at the sky and see images that are basically being lensed by massive objects. Now, that's an incredibly powerful idea, because we can then use the images to guess how much mass we're seeing. If I'm looking over here, I know that the strength of the lens depends on the mass. So I can use this to measure masses in the universe, right, independently of anything else. It's an incredible technique. So, yeah, this started out as a curious effect, and it became something that we thought, well, we could probably see this, and then we did see it, and then we actually just use it to measure stuff. And that's very much the progress of science. You know, sort of major curiosities today are just bread and butter physics in sometimes even 10, 15 years' time. Lawrence must have showed you this, did he? He just rotated it, right. So this is called the bullet cluster. This caused huge excitement a couple of years ago. You know, what you're getting in these lectures is science now, not science 100 years ago. And what we're seeing here is we're seeing galaxy clusters colliding side-on. We're just lucky enough here that these clusters have collided side-on. Now, let me explain what the pink and the blue are. The pink is what happens when the visible matter interacts. So I've got a galaxy cluster, and there's visible stuff in the cluster. And as that passes, you know, as the stuff here passes the stuff here, it starts interacting, and it heats up, and it emits X-rays, right? And so you get this, and it slows down, because if something's emitting X-rays, it's losing energy, right? So it slows down. And then we get this X-ray emission. So if we look in an X-ray telescope, we see the pink stuff here. What the blue region is the region that we get from gravitational lensing, right? We can use gravitational lenses to work out where the mass is in the system. And the mass is not concentrated near the visible matter. It's over here. So if I had a load of dark matter in the galaxy clusters, and I collide them, the visible matter gets trapped in the middle, and the other stuff just flies straight through, and you see the mass over here, right? So this is extremely good evidence that indeed we have some sort of dark matter in galaxy clusters, right? And the sorts of numbers you come out with in these studies for the amount of dark matter matches what Fritz-Vicky used to be seeing, so it's very compelling. It's very, very, very difficult to explain that with modified gravity. I would say it's impossible, actually. But, you know, there's error bars on these sorts of measurements, maybe that's it. But I think the final nail in the coffin for modified gravity is the cosmic microwave background observations. Now, Lawrence may or may not have gone into this detail. Did he tell you this? Why am I even here? Okay, I'm here to tell you other stuff that you'll hear later. Did he explain where the microwave background came from? Yes, he did. Okay, we'll pass through it quickly then, but I think it's worth seeing twice. The more times you see something, the more you understand it. So the microwave background tells us an enormous amount about the content of the universe. And to understand where it comes from, we have to look at the history of the universe. So the universe started with a Big Bang. I'm sure that's familiar to you. And it expanded from this tiny point. And first of all, it expanded really, really, really quickly. We call that inflation. It just sort of blew up massively. And then after that inflationary period, it starts expanding more slowly. So here's sort of size of universe roughly on this axis. And you can see it increases massively. And then suddenly it sort of starts expanding slower. Now, in the very early universe, it's so hot, and we touched on this morning, you can't even form nuclei, right? You have quarks flying around and gluons flying around. And then eventually, you start forming nuclei. And then eventually, you form atoms. And when you form atoms, something very significant happens. So the photon, remember, is the force particle of electromagnetism. That means that it interacts really, really strongly with anything that's electrically charged, by definition, in fact. So before you form atoms, you've got nuclei, and you've got electrons flying around. So what's the charge on a nucleus? Is it positive, neutral, or negative? Louder. It's positive, right. And what's the charge on an electron? Is it negative, positive, or... It's negative, right. So if I have photons, they can't move very far, on average, because they're constantly bouncing off charged objects, right? Now, as soon as I get cold enough to form atoms, I suddenly have all these neutral atoms and then all these photons sitting around. And there's now nothing to stop the photons, right? The photons can interact with atoms, but not very strongly, right? They could cause changes in energy state, presumably, but that doesn't happen very often. So what I find is that the photons are still traveling. You know, I mean, some of them have hit a star or something, but most of them haven't. So if we look out into space, all around us in every direction, there's microwaves coming to us at a fixed temperature, which are basically the microwaves from the early universe. And their wavelength shifts over time because the universe is expanding. So imagine having a wave, but where you're stretching the space. So the wavelength changes. So that's how we know that they're microwaves, and everything we calculate about these things basically turns out to be what we observe. It's really impressive. So we've spent a lot of time in the past, I guess 15, 20 years, taking very, very detailed photos of these microwaves with satellites. And we'll find out why. So this is called WMAP. This is actually out of date. There's been another one called Planck since this. But WMAP was the first one to take a really good photo. And this is what it took. So did you see this the other day? Yes. I mean, this, I think, is the single, I mean, even more than the Higgs discovery, this is the single most important picture in physics in the last 15 years. I said that we see microwaves coming all around us, and they're roughly the same temperature as we look around us in the sky. And the word roughly there is extremely important. What it means is if I zoom in 10,000 times, then I start to see slight differences in temperature. Right? That's why we spend lots of money putting satellites into space to do this. It takes that real precision to do this. So at the level of 1 in 10,000, we see these fluctuations. And these are crucial because these are the seeds of future structure formation in the universe. So think about how, with just using gravity, you can build structure in the universe. If a bit of the universe is slightly more dense than another bit, gravity is an attractive force, and it starts pulling in the matter, right? And there might be another slightly more dense bit over here, and it starts pulling in the matter, right? And so eventually you start forming stars and galaxies because you've got matter falling inwards faster and faster, and you can kick off all the nuclear reactions and stuff like this that you need to kick off. So what we can do is we have a very good mathematical description of what causes these bumps. Actually, it comes from quantum fluctuations, similar to the stuff we were talking about this morning. And if I relate that to the stuff in the universe, I can actually derive exactly what the universe is made of. So, you know, if you know anyone who's had a baby, they go to the hospital at 12 weeks and they get a scan of the fetus to see if anything's wrong. And we're basically seeing that scan for the universe in this photo, right? It's that we're seeing. It's completely amazing. I can't tell if it's a boy or a girl, but it is at least a universe. Okay, this is just the same data, incidentally. The job of a professional scientist is to take a picture that's really easy to understand and turn it into a picture that's impossible to understand, right? Without training, and that's why we justify our salaries, right? So what this is don't ignore anything about what this graph is telling you. The only thing I want to show you is that the data points here have very small error bars, and the theory of astrophysics that we have is the red line. And it agrees absolutely exactly. Right? If you were in school and you did an experiment that agreed that well, you would expect to sort of leave school with the Nobel Prize, not just your sort of high marks. Right? This is an absolutely incredible fit. So this is to convince you that we really understand the universe on very significant scales. We really understand what makes this thing tick. And what we've learned is this, that everything I showed you this morning in the table of particle physics is only 4% of the universe. So everything we did in the 20th century is only 4% of the universe, right? 23% is cold dark matter. That's this weird dark matter which made Fitzvicky angry and is still sort of keeping us busy. The other part of the universe is called dark energy. I suspect Lawrence mentioned this. And it's even weirder. So that's something that's causing the expansion of the universe to accelerate, right? The universe isn't just expanding at a fixed rate. It's expanding faster and faster and faster. And that was a Nobel Prize a few years ago, yes? Yeah, this is a really good question, and I can never quite remember the answer. Because basically, if you take all the matter out of the universe, it's still there. It's a fixed vacuum energy associated with space itself. So as space is expanding, naively, you're creating more energy, and you start to worry about conservation of energy. And there is an argument that conservation of energy is fine with this principle, and I can't remember what it is, I'm afraid. But I think it's okay. But it's very weird. It's like an anti-gravitational effect. You know, gravity is only ever attractive. So if I'm expanding a universe and it's full of mass and energy, that's trying to pull it back in, right? So there has to be some sort of anti-gravitational force. Yes? Is it possible that dark energy is like anti-gravity? Well, yes. Basically, yes. I mean, Einstein had this idea that in general relativity there was something called a cosmological constant, which was basically like an anti-gravity term. And he thought it was a massive mistake, and we've now found out it's almost what dark energy is, right? What we think, there are ideas about what could be causing this. It's some sort of new field in nature, but it's a very weak field. This acceleration isn't very dramatic. So I would say that in 50 years' time, I could be standing here or sitting here in a wheelchair or half robot or something, we still wouldn't understand dark energy. Dark matter, the reason I'm going to talk about that for the rest of the lecture is I really think in the next 15 years we're going to know what that is, right? And that's significant for you guys. So you're mostly year 11 and 12, is that correct? So in a year or two you'd be starting university, probably, and then 4 years from then you would be a researcher. And at that point, you could already be going to CERN, right? At the start of your PhD, you'll go to CERN if you come and work with me, for example. Because I don't want to go there all the time because I get jet lag. Right? But the point is that you would be doing that work, right? I mean, this work which is going on to this amazing, probably a Nobel Prize for whoever gets it, is for you to do, right? So you can definitely keep studying and solve these massively important problems. So do we know anything else about dark matter? We know a few things. We know it's cold, right? And that doesn't just mean that it woke up in Sydney this morning. Some of you from warmer climes must be ruining your decision to come here, but I hope you're enjoying it. It does get warmer eventually. It means it's slow-moving when galaxies form. Imagine trying to form a galaxy, and there's lots of hot matter flying around. Every time you think you've got this galaxy formed, it's blasted apart by the matter. So the matter, when galaxies are forming, has to be moving fairly slowly, right? And so we think dark matter is cold, and that's a technical term. It actually means non-relativistic. It means its speed is much less than the speed of light, for interest. I've already said it has to be electrically neutral, else it wouldn't be dark, right? It would be visible. It would be giving us photons. So it must be electrically neutral. It obviously has to be fairly stable, right? Because it's still sitting there. It was made in the early universe, and it's still there, sitting in galaxies. So it obviously has to be electrically neutral, and that means, stable. It has to be stable. So it can decay. I can write down theories of dark matter for you that will have decaying dark matter, but it is, the half-life, if you like, of that decay must be fairly long. We also expect it to be weakly interacting. To match the pattern of those fluctuations, it has to be weakly interacting. So that is, again, a precise technical term. It means its interaction rate is something like the weak force. So it's interacting mostly via these sort of weak force effects. It's not interacting strongly or electromagnetically. Right? So our favourite hypothesis is that dark matter is some sort of weakly interacting massive particle called a WIMP. The competing hypothesis in the literature for many years was machos. There were these sort of private jokes of a generally misogynist nature running in the literature. Machos would be sort of massive compact halo objects, I think is what they're called. So basically black holes. Black holes are pretty dark. They're black. So maybe dark matter is just black holes, but it turns out there's not enough of them. So I really think dark matter is a new sort of particle, and I think we should discover that in the next 10 or 15 years. And indeed, the paper I was writing in my hotel room yesterday was hypothesizing what it is and how you would be able to see it. So one place we can look for dark matter is the Large Hadron Collider. What we generally want to do, think of the example of how do we know there's hydrogen in the sun? Right, we know there's hydrogen in the sun because we've burnt hydrogen on Earth and it burns with a certain colour, and you get a spectrum if you put that through a prism, right? And then you look at the sun through a prism, at least hopefully you don't, you get a camera to look at the sun through a prism, right? And you see the same spectrum, and then you say, well, there must be hydrogen in the sun, right? So it's a two-step process. You do an experiment on Earth, and then you use those measurements to sort of correlate your astrophysical observation. So what we want to do with dark matter, ideally, is make dark matter in a laboratory, study its properties, and then to prove it's dark matter, we have to somehow see the matter that's in space and check its properties and check that it's the same thing. Right? Hopefully that's clear. We couldn't just do an experiment on the Earth. We have to prove that what we're seeing in space is the same as what we're making on the Earth. So as I said this morning, what happens at the Large Hadron Collider is we have this 27-kilometre tunnel. We throw protons around in one direction, protons around in the other. We smack them together. And what happens is quantum mechanics plus E equals mc squared. You get this sort of billion Kelvin proton soup, and anything can emerge from this. It didn't have to be inside the proton to start with. Anything, literally, can be made. And that anything could easily be dark matter, right? And that's what we're hoping to produce. And I'll explain over the next 20 minutes or so how we actually measure dark matter at the LHC. So the LHC is 100 meters under the surface of Geneva. It's actually 100 times more exciting than the surface of Geneva. I'm fairly lone in these opinions. I mean, my colleague said, can you stop saying Geneva's crap, because we're never going to get students to go to Geneva if we say it's crap. Has anyone been to Canberra? Yeah. Right, it's sort of like Canberra. It is, except there's less obnoxious people in it, in terms of politicians. I mean politicians, I don't mean you. I should stop having a go at politicians, given they pay my wages, actually. But, okay, no, Geneva can be very exciting. It's just Swiss, you know, and the Swiss have their own definition of exciting, which is not the Australian or British one. But it's on the French-Swiss border. So when I was there, I lived there for 2 years, and I lived in France, where the cheese and wine are plentiful and cheap. And then it's fantastic, so it's very good. So we have these two counter-rotating beams. We accelerate protons to near the speed of light. How do we do that? We have to use superconducting magnets. So here is a person. This is one of the jobs you can do at CERN. You can be a magnet engineer, effectively. And there she is, standing next to this magnet, sort of posing for a photo whilst being very busy, by the looks of it. They're cooled to 300 degrees below zero. That's below 0 Celsius. That's only just above the smallest temperature you can possibly have. Right? If you woke up cold this morning, you'll be reassured by the knowledge that there is a smallest temperature there can possibly be. Right? Your room can't keep getting colder. You'll be dead long before you reach it, but there is a minimum. We have about 800 million collisions per second, and that's significant. What we're trying to do is make see very rare things. Most of the time when you collide protons together, actually it's about as exciting as central Geneva. Right? They just sort of graze past each other, nothing really happens. Right? Very occasionally you might make a top quark or a W boson, but we saw them 30 years ago. They're not really exciting to us. What we really want to see is dark matter, or of course the Higgs boson, again, which we've now seen, and that's very rare. So the approach that we take is, look, if we're going to run this thing for 10 years, let's just collide the protons 800 million times every second. And then we'll get so many proton collisions that we're bound to see these rare things happen. Right? And if I see a Higgs boson, we didn't discover the Higgs boson by producing one of them. We produced thousands to tens of thousands of them, and we have to do it enough times that we're really sure we know what's going on. Right? Because in some sense, you're taking a statistical average of the events that you've seen. These slides say that we have 14 tera-electron volts per collision. It's actually 13 at the moment. The first time we ran the collider, it blew up. It was impressive, but one of these magnets, which weighs tons, was sort of shafted 100 meters down a corridor because it blew up. It turns out there was a bad solder between the magnets, and when you try and put 2,000 amps through something which is no longer superconducting, you get explosions. So we're gingerly running at 13 now, but that's already high enough, we think, to discover lots of new things. So have you seen the explanation of what a tera-electron volt is before? No, good, because I'm going to go through it, and I bet Lawrence didn't tell you that. Right, good. So we work in weird energy units. I mean, give me a unit of energy. Anybody? Joules. Joules, great. I mean, that is the common... Joules are the unit of energy that you are used to. The problem is the number of joules in the particle collision at the LHC is so small, it's a crap unit to use. So the electron volt, first of all, we have these 7 tera-electron volt protons in the beams. 1 tera-electron volt is 10 to the 12 electron volts. So the tera there is a bit like the killer in kilogram. It's called an SI prefix, and it's just saying that we have 10 to the 12 electron volts. And that's what this is. So have you seen the definition of an electron volt before? Yeah, you may have done. I mean, the force, basically the sort of energy released, if I release an electron and a potential difference, is the charge times the potential difference. So if I release an electron and let it go through a 1 volt potential difference, that defines what the electron volt is. Right? So it's actually 10 to the minus 19 joules. It's 0.6 times 10 to the minus 19 coulombs or whatever times 1 volt. So it's roughly 10 to the minus 19. So that means it's that number of joules. Right? A tera-electron volt then is 10 to the minus 7 joules. And again, this is just a unit. This is just the units that we use. It's nothing really fancy going on here. So 10 to the minus 7 joules is this number of joules. So each of my collisions at the LHC has a very, very, very small amount of energy. Right? That's why we don't use joules as a unit, because it would be horribly frustrating writing that every time we wrote a paper about 400 times. Right? So the thing is, it's really low energy, the LHC, and yet we call this high energy physics. So there's something going on here and we have to understand what it is. So what we're going to do quickly is just work out, typically, the kinetic energy of something which is about that number of joules. So, I've just ruined it. Who wants to tell me the formula for kinetic energy? You clever bastards. Very, very good. There we go, half mv squared. And I'm going to take something like a mosquito. Any idea how much a mosquito weighs? 10 grams. I'd say 1 gram because it's on my slide, but 10 grams is reasonable. Pretty ferocious mosquito would probably be about 10. So there we go. There is a mosquito mass. So we then want a typical velocity or speed. I mean, how fast? Let's say meters per second. How fast is it going to go? 10 meters per second. Do you think a mosquito could do 10 meters in 1 second? 0.2. Okay, I'm going to say 0.01. I think 10 centimeters per second is about right. Right? Now, amazingly, one of the plagues at CERN in the summer is mosquitoes. There's loads of them. And someone told me in the lab that the way they find you is that they're sensitive to extremely small gradients of carbon dioxide. So animals like us exhale carbon dioxide, and the mosquitoes sniff it out. They sort of fly randomly till they start sniffing the carbon dioxide. Then they follow the gradient to your skin, and then they bite you. Basically. So you can buy things that you plug in that confuse the mosquitoes by giving them bad smells, right? And that's what I did. But if you hear a mosquito and you close your eyes and then open them again, it could easily have gone 10 centimeters. So 10 centimeters per second is about right. So the kinetic energy is, what I've done here is v squared, just squared this thing, and then I've multiplied by the mass, and I've ignored the factor of a half, because again, I can't be bothered. So I've just put an approximate sign there. And then, lo and behold, I get 10 to the minus 7 joules. Right? So the energy of one collision at the LHC is about the energy of one proton that's coming in is carrying about the same energy as a mosquito. Right? So we could have easily just built a large mosquito collider, I suspect. It would take a long time to get 14 mosquitoes to hit each other, but it would cost less than 6 billion francs, probably. Yes?
Does this mean that you can completely annihilate mosquitoes using these protons?
If you could hit them, yes, probably. But I don't know if you'd be able to hit them. Right, so why is this, why does the LHC work at all? Clearly, we're not going to discover anything if we get mosquito, even if we could get them to fly into each other. Now, the answer rests in consideration of volume. Which contains more water, a droplet of water or an entire cloud of water? The cloud. The cloud has obviously got more water in it. If you've ever been to Manchester, when you're walking around, you're essentially walking through clouds. They just sit on the ground constantly. And that's what you get, right? But of course, the water droplet has a much higher density than a cloud, and that's how clouds eventually come undone. They get too dense, and it rains, basically, right? It's annoying giving this lecture in Australia because you don't get a chance to see this very often. In Britain, it's a daily occurrence. It's very convenient. So you basically get a lot more density in the water drop, and that's really the secret of the LHC. We take the energy of a mosquito, but we squeeze it into a space a million times smaller than a mosquito, right? So we don't just accelerate these protons with a superconducting magnet. We have to get them to hit each other, which is staggering. They talk about focusing the beams. They use beam optics to sort of control the behavior of these protons. And this is incredible ability. I mean, people like me have no idea how this works. We just let them get on with it. There's very few people in the world who do this stuff. If you want to be an accelerator physicist in Australia, it's quite easy to do. We have a synchrotron at Monash, and we're already signing deals with CERN to do accelerator research with them. So you can actually just work on the accelerator itself. That's quite a cool thing to do. So what we're making here is, it's really high energy density. It's not true to say it's high energy. And it's the energy density that is reproducing the conditions of the Big Bang. So that's why at the Large Hadron Collider, it's like we're looking back to the start of the universe, because we're making these regions of immense energy density. So here again is the collider, and you can see we've drawn a line here to show this is the main ring. And you can see another ring here. This is an old accelerator that CERN used in the 50s and 60s and 70s. And they never waste anything. It's recycling in action. We just now use that as an injector for this. So the protons get a fun trip where they sort of get to go around here and get quicker and quicker, and then they're released into the big ring. Now, we have detectors at different parts of the ring. You don't just smack the protons together once because you've got so much energy in the system. You may as well smack them together 4 times. 2 of the detectors are designed to just say, look, if there's anything new, we want to discover it. So, this is ATLAS, which I work on. This is CMS. And they were the ones that found the Higgs boson. If there's dark matter, they're the ones that will find dark matter. Right. Then there's some specialist experiments. This thing here is called LHCb. There's a mystery in the universe that it's mostly made of matter and not antimatter. And we sort of understand how that might work, but this experiment will tell us more. Yes? A good idea. A good question, rather. Lots of people over many years. What happens is, I mean, as I'll say in a minute, there's 2 things going on here. There's the actual accelerator itself, and there's the design of these things. And the basic design of these things hasn't changed in about 30 years. We're just building bigger and bigger versions. And so when it comes time to build a new one, you chat to your friends in the detector community, and they say, well, this is the latest technology that you should be using. And we get lots of people to try out all the different technologies. And we do R&D on small setups, and then we decide. And nowadays, we do lots and lots of computer simulation as well. And the same really happens for the magnets. The accelerator physicists say, well, look, if we use this technology, we can probably get it working, and it will take us 10 years, and it will cost this much, and you price it all up. And then someone somewhere has the final sign-off, and I guess in this case it's the CERN Director General, right? So there's one more sort of specialist experiment that's called ALICE. Every Christmas, just for kicks, we take the protons out and smash heavy ions together. And you get this very weird state of matter called a quark-gluon plasma, which existed in the early universe, and they study that. And this is just crazy. I mean, it's like doing fluid mechanics in a detector with this billion sort of Kelvin proton soup. And I don't know how anyone even thinks they understand how that works. And I guess they don't. But there's a group in New Zealand who do this, for those who are here from New Zealand. So here's the ATLAS experiment here. In terms of ATLAS and CMS, they can both do similar physics, and more or less with the same precision. There's one brilliant thing you should learn, and that's that here is ATLAS. The CERN canteen is about a 5-minute walk over here. CMS is a few miles that way. Right? It simplifies your life considerably to be on ATLAS, right? Because there's croissants, beer, and steak and chips down here. Sometimes all at once. If you look at the detector, I remember starting my PhD and being shown this thing, and I thought, well, how on earth does this work? It's a very complicated device. In fact, as I say, the basic design hasn't changed probably in 30 years or so. The middle of this machine measures the momentum of particles, and the outside measures the energy. And it turns out in relativity, if you know the momentum and the energy of anything, you can work out what produced it. So remember, the protons are coming in, they make this weird proton soup. Anything can pop out of the soup, and it decays almost instantly. All of these exotic particles are unstable. So a Higgs boson decays so quickly you don't even, you just see the decay products. And if I know the energy and the momentum, they then fly through here. I might get 2 photons from a Higgs, for example, and they'll just fly out through this machine. And if I measure the energy and the momentum of the photons, I can actually get the mass of the Higgs. So that's how we know that the Higgs is 125 giga-electron volts, right? Because we measured the photons, and then we measured the mass. And indeed, this paper I was working on was explaining why the mass is 125. So, here's just the same thing sort of going out. You build this thing in layers, and as the particles go out, there's something called a tracking detector, which measures tracks, and that gives us the momentum. And I will actually show you the maths in a minute of how you measure momentum from a track. Yes, sorry, question at the back. Yeah. Yes, right. So, in one sense, the basic design hasn't changed, which is that you basically, you design these sorts of experiments in the same way. In fact, the detectors at the LHC are now going to sit there for 10 years or so. When we turned it off in 2012 for a couple of, until now, basically that was to stop it blowing up when we went to higher energy. So initially we tried to get to 14 tera-electron volts, and we hit, I can't remember what energy we actually got to, maybe 8 or 9 or something. I think it was 10. We got up to 10, and then it blew up. And what they found is that they could get it running at 7 or 8 tera-electron volts without warming the whole thing up. Because this thing is super cooled, it takes a year just to heat and cool this thing. right? So if they had to warm the whole thing up, there was no physics that could be done for years. And what they said was, well, we can sort of keep it running at lower energy, and it's safe. But then we're going to have to stop for 2 years to take it up to high energy and fix all the bad solders. So that's what they were actually doing. Nevertheless, what we did in the ATLAS detector is we slid another piece of detector into the middle of it. And so we now have an extra piece of detector. And I think it's mostly been successful. The project leader of this, I was chatting to CERN 2 weeks ago, and he said, well, we're sort of seeing this sort of thing with it. So I think it's moving a bit, which is bad news. But they'll sort that out fairly quickly. OK, so going outwards from the middle, we have this sort of tracking device here. That measures momentum. Then we have basically energy buckets. The way you measure the energy of a particle is you stop the particle. You use a material which stops a particle, and then you measure how much energy it released as you stopped it, right? And you can even design buckets for different things. So the first bucket here stops photons, and it stops basically electrons, right? And then this bucket stops anything that was caused by a quark. Quarks sort of behave oddly, but we can, more or less, it's true to say that we stop quarks in here, right? And so we can even tell what sort of particles we're seeing. Because if it stopped here, you know, and as I look at an event, I'll work out where the particle stopped. If it stopped here, it's probably an electron or a photon. And if it stopped here, it's a quarky thing. And then muons just fly through all of this. So we actually have special machines for muons out here, right? So how do we measure the position of these particles? I said that we have a tracker. So what happens is, as a charged particle goes through the tracking system is mostly built out of silicon, right? And you can make something special in silicon called a PN junction. You probably haven't heard of this term. But it's a special thing I can make out of silicon. And it's great, because if a charged particle goes through this piece of silicon, it releases a small electric current, right? So what I do is I just build lots of strips of silicon, and then as this particle is going through, like this, I get a little dot of electric current every time it passes through. So then after the fact, I can just look at the dots, and I can basically work out exactly where the particle went. You know, when you see photos in textbooks, they used to use bubble chambers for this. They would literally have a sort of some horrible emulsion in a chamber, and a particle would go through, and you'd see a track, and you'd take a photo. And there's an old experiment in your third year at Cambridge, you can actually do an experiment where they get all the slides out the basement and project them on the wall, and you have to use a ruler to measure momentum, right? Now, the trouble is, you can't do that 800 million times a second, right? Not even with the number of PhD students that we have on ATLAS. So you basically have to design some sort of automatic system, and this is basically a digital camera, right? It's a piece of silicon that's releasing electric current when something goes through it. So here it is. You know, here's a diagram of the tracker, and you can see it's here, and you can actually see a bit of it here. So what you do is you design one module of silicon, and then you just make 4,700 of them, and then you just glue them to a barrel and some end caps, right? And in total, there are 6 million strips of silicon here, and we've had to calibrate them all separately. Yes?
Earlier you said that dark matter is electric.
Yes.
So how is the silicon?
Right. That's actually a brilliant question, and we're going to come back to it, right? But I don't want to spoil the answer now. But that's very perceptive. What you've basically said is, you're talking rubbish. You can't see dark matter, and indeed I am. But you'll see why it's not rubbish later. Right. Excellent. So here are the modules of silicon. We had to calibrate those 6 million strips separately. So my first job, one of them as a researcher, was to write the software which looked at this thing and told you if it was working properly, and looked at every single one of the 6 million strips and then said if there was a problem. And every week I had to give sort of 3 talks that told people if we'd seen any problems. And so I even wrote a program that wrote the talk for me. That's what, when you get good at computers, this is the sort of thing you can do. So I could then just go to the pub, come back, and my talk was written with all the results. And I was going to sync it up to Stephen Hawking's voice, but I couldn't get, I didn't have sound on my laptop at the time. But this thing, yeah, these things have to be aligned sort of to millimeter scales, maybe even micrometer. I can't remember. I should remember. This is a long time ago. So that was done in Oxford, right? They glued that barrel together in Oxford. Then they drove it over mountains to CERN. And they have to make sure this thing hasn't misaligned itself or wobbled or something. So none of this should be possible at all. That's what I want to say to you. And it is. So if you're interested in bits of silicon, if you're a detector physicist, solid-state physicist in training, you can do that. And that can be your career. Yes?
What are the 420,000 xenon straws?
420,000 xenon straws. That's actually a good idea. That sounds like it's for the TRT. So we actually have a transition radiation tracker. We have another type of tracking system which isn't made of silicon and sits on the outside, and that's got these straws in, basically. And that uses a slightly different technology. So what the silicon does is it gives you relatively few tracking points, but at very, very high precision. And then what that thing does is it gives you a very low precision on each point, but it gives you many more of them. And if you put the two together, you get a really good measurement of the track. Yep. I think a lot of people wished we'd just gone for an entire silicon system, because it's easier, but it's just much more expensive. You can't afford it, basically. This is what one module of the silicon looks like, and there's 6 computer chips here that read this thing out, so that's what I was writing a computer program to talk to. This is just sort of more, this could be Nikev in the Netherlands, or it could be CERN, I don't know. My brother used to work at Nikev. I have a twin brother who's also a physicist. He once went out drinking for a night and didn't realize that the next day was the annual pickled herring lunch, and didn't have a very good time. Right, so let's think about how we actually take these measurements and measure momentum. What's the formula for momentum? mv. Right, obviously. Now, this one's a bit harder. If I have a charged particle that's moving in a magnetic field, have you studied the force law on it? There's a force if I have a charged particle in a magnetic field. Anyone know it? Yeah, it is basically that, but you can write it in a different form. You can also write BQV, right? But it's related to the other one, essentially. So if I have a magnetic field and a certain charge and a velocity, that's the force on the particle. And the direction of the force is given by one of these stupid hand laws that you have to learn. I think we're making good progress in physics generally in representing people, but most of physics is still closed to people who don't have hands, which I find annoying. If you take your hand, the field points along your first finger. They're always highly contrived. The current points along your second finger. The thrust points along your thumb. That's a contrived way of saying force. Now, if I have a charged particle moving, of course, the current is aligned with the movement of that charge, because that's what current is. So the key thing to notice here is that, indeed, I actually get a force at right angles to the direction of motion. Right? Now, what happens when I get a force at right angles to the direction of motion? I get circular motion. Right? The thing moves in a circle. And so I have an equation for the centripetal force, which is what? mv squared over r. Very, very good. Very good. Now, I'm not going to go through all of the steps, but you could easily sit and put those equations together, and you can work out that momentum is equal to b times q times r. That's just if I sit and put those equations together. So basically, if I want to measure the momentum of something, and I know the charge of these particles, they're basically electrons, so it's one electron charge. If I've measured a track that's a segment of a circle, I can work out the radius of curvature just from the geometry, just from this property. So I measure this, and if I apply a magnetic field, then I can get the momentum of the particle. So that's how these tracking systems work, right? So I have to apply a field, and then because I know the charge and I've measured the radius, I can get the momentum. Now the problem is, these particles are moving at nearly the speed of light, right? So to bend a particle that's moving at nearly the speed of light, you need a very, very strong magnetic field. So this is our main magnet, our solenoid magnet. Here's a person who himself is not very small, right? He's a sort of quite tall person. I'm trying to think. I went to, they had an Acme, they had an exhibition of like Tim Burton film stuff, and they had Johnny Depp's Batman costume or something, right? No, he wasn't Batman, who was he? Pirates of the Caribbean. Right, they had Michelle Pfeiffer's Catwoman thing, and then they had Pirates. Now Johnny Depp is about that tall. Is what I get from his clothes. So Johnny Depp's probably about there. This is a tall CERN, strapping CERN physicist. So look, I mean, this thing is huge. It's 5.7 tons. It's a 2 Tesla field. When you see bar magnets, you're looking at millions and millions of weaker in terms of the field. It's about 6 tons. It's huge. Remember that this thing has to go underground. And the only way to get it underground is to tie ropes to it and lower it very carefully and very slowly. And if you drop it, the whole experiment's destroyed and will never be built again. Right? I mean, CERN has money. It doesn't have that much money. It can't replace things. So it was a very delicate time when we were trying to get these things down to the cavern. We have other sorts of magnets. We want to bend the muons when we measure the muons at the outside of the experiment, and we use these sorts of magnets for that. And there's some other sorts of magnets we have flying around. So I was actually at CERN. They lowered this NCAP magnet. Now, this thing had to be driven, I think, from Italy, again, over mountains. But it turns out that it was so delicate, this thing, that if you tilted it more than about a degree, it would break. Right? So they had it on some sort of thing which corrected for the motion of the truck as it went up and down hills. Now, if you've seen Italians drive, right, the fact that it's just, again, it shouldn't work. And we watched this, and this was lowered very, very slowly. They have people abseiling down here. You can't see them here, but for the other magnets, they were abseiling down to make sure it didn't break. Here's one of the toroid magnets. Just phenomenal engineering. So again, if you're an engineer, go and work at CERN. You don't have to be a physicist. We need the best engineers in the world to do this stuff. So I said basically we measure energy. So we have the momentum, right? We just need the energy. We measure the energy by stopping particles, and this is just a big bucket which will eventually fill with stuff. It's now full, of course. This was taken years ago. And you have sort of scintillating tiles so that you stop something and it releases light and radiation, and you can pick that up using special detectors, and then you can measure the energy. So actually, I'm not an expert on that stuff at all. I'm an expert on the silicon, but I know something about it. I know very little about this. Right? Yes?
For things like energy and time and stuff, does that's a principle to play that?
So on this, yeah, it's a good question. On this scale, actually not. You actually have things which sort of give you a fairly well-defined amount of energy. Now, what's happening is that you're seeing something emerge as a physical particle, and it is sort of classical enough in this regime that you can treat this as if it's almost a classical process. Of course, it's actually losing energy quantum mechanically, but when you actually sum up the sum of the small energy deposits you've seen, you end up getting a well-defined answer, right? So for these sorts of interactions, again, we talked this morning about sometimes you actually need to do the quantum mechanics, sometimes you get an answer, using normal theory. The one thing I will say, though, is that all of this is relativistic. These particles are going at near the speed of light. So when I talk about the energy and the momentum, it's the relativistic energy, which is the formula we saw this morning, and the relativistic momentum that we're actually measuring. So it's not just mv, and it's not just mv squared, or half mv squared. I mean, this is just a picture of what the muon detectors look like. We just have these special things which catch muons as they go to the outside. And again, I'm not a particular expert in this. I think we're about to see a muon. It's not the most thrilling graphic ever produced, I would suggest. So now we can measure position and momentum and energy, and we can even say if something's a muon or if it's an electron or a photon or it's a quarky thing. And that really allows us to do physics, and that's how we do it. Now, a very large amount of the physics that we do at ATLAS is just first-year special relativity. Right? So indeed, you can still write research papers using first-year special relativity, so pay attention next year. It may be that there's a research topic that you can actually think of and write. Obviously, what we want to do at this point is explain how we would see dark matter at the LHC. So as we saw earlier in a perceptive question, we think that there's new particles in nature. The standard model can't explain everything. Some of them would be dark matter, potentially. And so what we want to do is measure the mass of the dark matter and how strongly it interacts with other things. So if we can do that at the Large Hadron Collider, we can then look at our astrophysical observations and see if it's consistent. But we really want to get these properties, but there is a snag, unfortunately, and that's, of course, that dark matter is invisible. Right? It's weakly interacting, and this is why the question was quite perceptive. It just flies out of this detector unseen. I mean, so do neutrinos. We make neutrinos all the time at the LHC, and they just disappear as well. So you are perfectly right to ask, how on earth do you measure the properties of a completely invisible particle? At the moment, I'm scratching my brains. I'm going to show you vaguely what you do in a minute. And there's different cases. There's different types of invisible, it turns out. And I lost a night of sleep because I thought I'd found a brilliant way to measure a particular type of invisible thing. And it turned out it was just complete nonsense. And that's why no one had thought of it before, because it was wrong. But there are things you can do, and we'll see them shortly. By analogy, I think there's a historical precedent, which is the invisible man, right? when you go to, and there's loads of variants of this film and book, but if originally due to H.G. Wells, but lots of people have done it. I guess the most recent was probably Hollow Man, the Paul Verhoeven film. People went to see this even though you couldn't see the Invisible Man, right? And by the end of the film, they thought they'd got to know him, and so you're never seeing the Invisible Man. What you're seeing is his interactions with other things, and that's how you learn this tragic story, right? But you definitely know the Invisible Man is there. Now, to be fair, the film is called The Invisible Man, right? So you are tipped off that there might be a man there who's invisible, right? But they could be lying, right? So the same thing happens at the Large Hadron Collider. If I write down any theory of dark matter that would be visible at the LHC, I never produce just dark matter. I always produce dark matter and something else, right? Usually some quarks or something, right? But possibly some leptons. So that's a posh word for an electron or a muon. So I always see something at the same time as I see the dark matter, and that's very significant. In fact, having said I wouldn't use this, Chris, would you mind getting this thing working? I'll just draw a diagram. How much time have we got left, roughly?
We have 20 to 6. So
Okay, we have time, I think, just.
So you want that one on? 3, 2, 1.
Perfect, excellent. Right, so we know that momentum is a vector, right? And so what's happening initially, and conservation of momentum is still true in relativity, incidentally. Yeah. Perfect, I told you it was invisible. Right, I have a proton coming in there, and I have a proton coming in there, and I'm going to make this the z direction. And this plane here contains the x and y directions, right? I'm going to blow my nose as well, which is going to do horrible things to the microphone. I was actually slightly disappointed then. Didn't even need to blow it, just did it for fun. So, what is the momentum in this plane before the collision? 0. Right? What's the momentum in this plane after the collision? 0. I've just told you, momentum is still conserved. Relativity doesn't break that. So that's very important. I can actually measure the momentum in this plane after the collision. The complication is I don't exactly know the momentum along this direction because the proton is a composite object. And so some bit of proton hits some other bit of proton, but there's a totally unknown component along this direction. So ignore that, but I can definitely look at this plane, and the momentum was 0 before, and it's 0 afterwards. So if I then look in this plane, and when you see these sorts of circles with the detector, that's what you're doing, right? You have all your detector components here, and you're looking in this plane. If I see a particle come out like this, maybe that's some sort of quark, and I see a particle come out here, and that's some sort of other quark. Does that momentum add up to 0? No. And so that tells me that there must have been something else produced, and that's quite possibly dark matter, right? Now, even more amazingly, I can actually get the mass of this particle, usually, and I can get its interaction strength just from measuring the properties of these things, once I've seen enough of them, right? So I can really, it's like the Invisible Man, I can get to know this very easily by studying the things I actually see. And it used to be thought that you couldn't do that, particularly well at the LHC, and I wrote some early papers on this, and other people did other better papers on this, I would say. It is very possible to do this, actually. So that's how we measure dark matter. Now, here's a cartoon of a particular sort of dark matter process. This is what happens if something called supersymmetry is true. Some theories of beyond the standard model physics give us lots of new particles, and we could produce lots of particles, and they all decay almost instantaneously, and they make a dark matter particle, and then we see all of this stuff. So these are quarks, this is maybe an electron or a muon, this is maybe an electron or a muon. And so if I measure these properties, I can basically get the properties of the dark matter. And we're still trying to invent clever ways to do this, right? And so I have all sorts of students working on these problems and looking at the observations we've seen to see if certain types of dark matter are now ruled out. So as I said earlier, the LHC at most will just give us the dark matter mass and the interaction strengths. But if we really want to prove that we've seen dark matter and not just a new particle, we have to try and compare the LHC measurements with measurements in space. I want to spend maybe the last 5 minutes or so telling you about the space measurements that we do. The simplest thing you can do is just grab a big tank of stuff. And dark matter is weakly interacting, but if I put enough stuff in its way, it will interact at some point, right? Now, the key thing is that there's dark matter in space, and the Earth is in space, right? So the Earth is technically flying through dark matter, right? So if I put a tank of stuff on the Earth, occasionally some dark matter will fly through it and the tank will wobble slightly, right? And so I literally get a tank of stuff, I usually cool it down, you know, and I stick it somewhere, and I spend 3 years watching it to see if it wobbles, right? And if it wobbles, I've probably seen dark matter. Now the problem is, you know, if I put this here, it may not look like it, but it is wobbling, right? There is some motion of this thing. And, you know, there are various processes at finite temperature that will always induce some wobbling in this detector, because of course, we're actually talking about absurdly precise wobbling that we're looking for. So you have to really understand exactly what it is in this tank of stuff that can wobble, and whether the dark matter wobble is any different to try and see dark matter. Yes? You could, but it would still wobble, because the biggest effect that you see actually is that there's always some trace radioactivity in any material that you can never really get rid of. And so what will happen is that you will find that some radioactive decay happens, and you get a signal in your detector, but it's just a radioactive decay. And you can never get rid of them. The only thing you can do is sort of count how many times they happen to see if it's roughly consistent. So it's all about how you characterize the background to look for the signal. So generally, we just cool them down to try and get the thermal motion reduced and stick them underground, right? Yeah.
Sorry to interrupt.
Yeah.
We are going to have to wrap up really soon because we have got to get on the buses.
Yes, I think I have about 2 or 3 slides. That's good. Okay. So we're doing this sort of thing in Australia soon as well. This is very popular nowadays. The other thing you can do is called an indirect search. This is, I guess, the last thing I'll talk about. So what you do here is, where do we expect there to be lots of dark matter in space? If I actually look at galaxies, then I have the sort of amount of dark matter in the profile of the galaxy going out in radius is something like this. So, you know, if I have a typical galaxy like this, I'm, you know, going out in radius in this direction, right? So we think the dark matter is concentrated in the center of the galaxies, right? That's where we think the dark matter is. So if I look at the center of our galaxy or distant galaxies, I should be able to see where most of the dark matter is. And most of the theories of dark matter that we write down actually do have some funky interaction. So, for example, dark matter could hit another dark matter particle and make a Higgs boson. And that could decay to 2 quarks, and then eventually these quarks give us photons. So there's no direct interaction between the dark matter and the photon. It goes through this other stuff. But we should be able to see a very high energy stream of photons. I won't take questions until I know we have time, I'm afraid. We then get this stream of gamma rays, and so we can actually stick gamma ray telescopes on the ground. When a gamma ray hits the upper atmosphere, I get a cone of light called Cherenkov radiation, and I can just stick dishes which are sensitive to gamma rays on the ground and image this system. They're sensitive to Cherenkov light. So here's an example in Hess, and if I take all these dishes, I can actually get an image in each of them that points back to where the gamma ray came from. So this is called an indirect search for dark matter, because we're trying to find dark matter annihilating in the galactic center or in a distant galaxy. And so I mention this because Australia has just become involved with this thing, which is really the LHC of gamma ray astronomy. This is called the Cherenkov telescope array. It's being built at the moment and designed. It will have lots of different dishes of different sizes, and it will have an awesome energy resolution and angular resolution to hunt for dark matter in galaxies. And so this is a very exciting topic, and it's just starting up here, if you want to do this sort of thing. So much to Chris's relief, I finished there. It's been a lot of fun talking to you. I think I probably have enough energy to join you on your boat trip tonight, so I can hopefully chat to some of you on the boat. Yes, basically, there's an amazing, amazing physics happening, and you can personally do it. That's what I want to finish on. Okay.